And we're going to finish up section 4 today and then do section 5 also. But first, we have a question. The homework problem says, in this in chapter 4, section 3, question number 8. It says, find the quadratic equation f of x equals ax squared bx plus c that goes to the point 5, 0 and has a local minimum at 0, -1. So what does all this stuff tell us? What does this tell us? What if it goes through the point 5, 0? What does that tell us? What would that point look like? One of the x-intercepts. Could it be a vertex? Don't know. Well, is there another vertex? I mean, another x-intercept? If this is a local minimum at this point, let's see what the graph looks like first. 1, 2, 3, 4, 5. So what do we know if we have this? If it has a local minimum at this one, it's a quadratic equation. That means the local minimum is also the vertex. Does the graph open up or down? It opens up. Because if it's a minimum, it has to be the lowest point. And we have an x-intercept at 5, 0. So what else can you tell me about what's missing now? There's other x-intercept, which is where? Y. Why does it have to be there? Because the quadratic equation is symmetric about the x value of the vertex is called the what? Axis of symmetry, right? Very good. Which means it has to be a mirror image. Since that's an x-intercept, this is local min, that means we have to have a graph that looks like this. So we have our x-intercepts at -5, and we have an x-intercept at 5. Set those equal to 0. If this is how we'd solve it algebraically. This would give us x squared minus 25 equals 0. But is that the right graph for that? No, what's missing? What did we take into consideration? So if x is 0, what is this one called then? That's the y-intercept. The y-intercept is the c value. So what we know so far about our graph it's shifted down one. What else? If it goes, if that's the local minimum, how do we find this value? How do you find the maximum minima? We just talked about it last couple of days. How do you find the extrema? Right. The first derivative equals 0. So that means the first derivative of our function set it equal to 0. So what's that going to find for us? Remember, it's the y value. Then what else do we know about a quadratic equation? So we know the y-intercept is this constant value. Since that's 0, that's the y-intercept. It's also the vertex. It's the local minimum. So what else do we know about this stuff? So we start building our equations from there. What do we know about the concavity? It has no point of inflection. Point of inflection only occurs when you have concave up and concave down. It's the point where they switch. Since this is a parabolic graph, it has no. So that means the second derivative, since it opens up, has to be greater than 0. So the second derivative of our function is 2a. And that's got to be positive. Okay, so far so good. We know the facts of this thing. The second derivative, concavity, has to be up. The first derivative is the slope of the curve. We know the slope of the curve is 0 at point 0, -1. So that means all this has to equal -1. What else do we know? Well, hold on. We know the first derivative is equal to 0. That tells us our vertex, where the slope equals 0. And the first derivative is 2ax plus b. We know it's 0. So what else do we know about that? Let's put together everything we've discussed last couple of days. The vertex occurs where the first derivative equals 0. Remember, once you get the first derivative set it equal to 0, what's that going to find for you? Okay, that's critical point, but it gives you the x value where that occurs. We'll come back to this in a second. Let's look at let's find everything about this one. Let's find the x-intercept. Let's find the y-intercept. Let's find the vertex. In algebra, remember how we found the vertex? The formula was negative b over 2a, and whatever that was, you plugged it back inside there. But the vertex occurs at f prime equals 0. Okay, so let's look at the algebra part. So we know that the x value of the vertex is negative b over 2a. So in this case, it's 1, 5, and 6. So the x value, the axis of symmetry, the vertex occurs at negative 5 over 2. And then what do we do at this value? To find the y value, we plug it back into our original equation. But we see we have an x value of the vertex. We know the equation. It's this. In our example, what is our vertex? 0, negative 1. 0, if this is equal to 0, what's the only way that can equal 0? So we know b is 0. Okay, so we have the vertex here at negative 5 over 2, and whatever y value that equates to. So we know that the first derivative is if it's equal to 0, then it's the vertex. Yes, okay, yeah, we know that. But more so, it's the x value that does that. It's the x value inside the function that makes it equal 0. So it tells you where the axis of symmetry. Check, we found that. How do we use the other information? We have, in our case here, we have an x-intercept. We have this part. Do we know the y-intercept? In our example? Yeah, the y-intercept occurs where x is 0. So we have x-intercept, y-intercept, vertex, axis of symmetry. Because what we have to do is we have to build our information from there. Whereas what we have to do from all this, we have to build these three values. And we found B already because the vertex was at 0, -1. And that's also the y-intercept. So we know when x is 0, y has to equal -1. So that's the C value. So the problem now comes, what is my A value? Well, we know it's positive. How do we know it's positive? Because it opens upwards. We just need a value. So how do we find that? What part will help us find the A value? What we could do, hear me out. You could work your way backwards. What does this formula find for you? The x-intercepts, the roots, the solutions. We know B is 0, C is -1. What is the x-intercept? Well, we know for sure it's 5 for sure. So we know that's 5. That's 0. 0 minus 4a. C is -1 over 2a. So let's go with that. Let's go with there. For a. Okay, so we have this so far. The square root of 4 is 2, square root of 8. So where do we go from here? What are we solving for? A. We're trying to get A by itself. So we have a radical. We can't have that. So how do we get rid of the radical? You could square. We should have here. We had 10a equals plus or minus. We could have squared both sides. So we have 100a squared plus or minus 4a equals 0. So if we do it this way, we have a is equal to 0, a is equal to 1/25th, a is equal to 0, a is equal to positive 1/25th. So 0 can't work. Why? It wouldn't be quadratic anymore. This one doesn't work. Why? It's negative. So our a value has to be, again, which satisfies our conditions for having a wided opening parabola. The smaller, the bigger a is, the more narrow it becomes. The smaller a is, the more wide it becomes. So we know a is 1/25th. We know c is -1, and we know the b is 0 from that. So our polynomial x squared minus 1. Would that satisfy our conditions for our answers? Well, this is the difference of two squares. It's x over 5 squared, x over 5 plus 1, x over 5 minus 1. Set these equal to 0. So we have x over 5 equals -1, x over 5 equals +1. Multiply both sides by 5. X equals -5, x equals 5, which is what we said our x-intercepts were. So how do we solve? Again, what were our processes? Mostly algebraic. The only thing we really need to know is what was the first derivative would give us the values of a and b to find the vertex. So that is my polynomial. Actually, it'd be x squared over 25. Okay. Yeah, the next section is what I want to get to try to get to today. Where did we leave off last? What was the last example we did yesterday? Example 4 or higher? We did example 3? We do example 4? Okay. Okay, good. Thank you. Recap. What does f of x tell us? Points on the curve gives us the points. What else does it tell us? Domain, range. Yeah, the whole list of stuff we had yesterday. First derivative, what do we use that for? Slope, and also find the vertex. And the second derivative, concavity, and the point of inflection. If you think about it, they're pretty much the same thing. How do you find the vertex? First derivative set equals 0. How do you find the point of inflection? Second derivative set equals 0. So it's the rate of change set equals 0. It's the change of the rate of change set equals 0. Example 4. Find the POI of the following function. F of x equals x power 5 over 3. What do we know that graph's going to look like? What do we know about it? Is it increasing or decreasing? It's increasing. Do the ends point the same direction or opposite directions? Opposite because they're odd. It's an odd exponent. So we know the graph will look something like this. So we're looking at something like a cubic function. To find the point of inflection, we got to find the second derivative and set it equal to 0. So makes it 2 over 3. Then the second derivative would be 5 over 3 times 2 over 3 x to the negative 1/3, which makes it 10 over 9 x to the power negative 1/3. So what's the point of inflection? Can you set it equal to 0? This equation will look like that. Can it equal 0? No. So it has no point of inflection. Although it should. If you think about it, if it looks like this, isn't this concave down? Isn't this part concave up? Shouldn't there be a point of inflection somewhere between there? It's an increasing function. So what do we look for there? How would we figure out what we need to know here? So what happens? Okay, so we look at the second derivative, or this one here. What happens when x is negative? What happens when x is positive? Since we can't set it equal to 0 and find it that way, now we have to localize it. Because it's an odd function, when I put a negative number, and can I take a negative number, a cube root of a negative number? Yeah. What does it become? Positive or negative? Stays negative. So if I plug in a negative number in there, the second derivative is less than 0, which means it's concave down, which is what we thought. If it's greater than 0, I put a positive number in there, it stays positive, so the number remains positive, so it's concave up. So that goes us, if it's less than 0 or positive, what happens at 0? That is where the point of inflection has to be. Because if the negative numbers are concave down, positive numbers concave up, that means that 0 has to be the point of inflection. That's where they change, even though we can't set it equal to 0. This just shows you that the point of inflection doesn't really have to exist through this formula. This is an example of where it happens. We have to extrapolate what's happening. What's with all these weird questions today? Let's hope this one gives us something. Find the point of inflection of this one. Yay! So we have to find what? The second derivative. Set that equal to 0. And it equals 0 when x is 0. So is that the point of inflection? Trick question. Well, let's see. Well, does this satisfy with what we're saying here? Point of inflection has to be between two set different concavities. Let's look at this one. If x is less than 0, if x is greater than 0, if x is less than 0, what is the second derivative? If I square it, it stays positive. If it's greater than 0 and I square it, the second derivative is positive. What does the graph look like for x to the fourth? Looks like x squared. It's concave up here, it's concave up here, it's concave up here. It's concave up everywhere because it's a parabola. So what is our solution? The point of inflection does not exist. Because it's concave up everywhere. See, this is, now, I'm glad these last couple of examples, and even the question that Ryan asked, they're excellent because These are all thinking questions. The question that Ryan asked, we start off class today. If we looked at it algebraically, if we had the x-intercept and we know it's symmetric, we have to know the other x-intercept. From algebra, we said just take those two x-intercepts, set them equal to 0, and solve. So we have x plus 5, x minus 5, get it equal to 0, and we have a parabola. But that's not what's happening. So, and that's what these are doing here. We come up with a solution. The second derivative does equal 0 at 0, but it's not happening, not true, because in order to be a point of inflection, you have to have opposite concavities on both sides of that point of inflection. The same as in the first derivative. If we have a maximum, what has to be true? So if we have a maximum at this point C, then what has to be true? Well, all the points to the left of C, the first derivative has to be positive. And for all the values on the right-hand side of C, the first derivative has to be negative. That just goes with the definitions of what maximum minima are about. If it's a minimum at C, for all the points to the left of it, the first derivative has to be negative. And on the other side, first derivative has to be positive. So we have to not only trust the numbers we're getting, we have to verify the numbers by proving the definition of what we're looking at. Okay, any questions so far? All right, let's look at the next example. Graph this function, or the cube root of x. Find the point of inflection. So the first derivative will give us what? Remember, we subtract 1, which is subtract 3 over 3. And the second derivative I'm going to have to negative 2. Negative 2 over 9. So what this one looks like, set it equal to 0. So can we expand our definition, or the points we're looking for, like we did for the first derivative? Not only do we find out where it's 0, but we look at the points where it's undefined. Because where is this equation undefined? Now, if it's undefined at x equals 0, what does that tell us? Why is that the case? Well, let's look at 0. Let's look at the first derivative. At the first derivative, we have so when x is 0, what does this number become? It becomes undefined, but it's undefined because it goes to where? It goes to infinity. It's undefined, yes. So if the slope is undefined, what does that mean the graph looks like? If it was a constant, it'd be 0, the derivative. So the slope being undefined looks like what? It's always going to be a line. What kind of line? It's a vertical line. If it's a horizontal line, it's 0. It's a vertical line, it's undefined. Bless you. So what this tells us, because our second derivative, it's undefined at 0, it's undefined at 0 because we have a vertical line at 0. And that's what our graph is going to look like. The cube root of x looks like this. So what happens at 0? Well, this tells us that we have a vertical line at 0. Does it have a point of inflection? At the origin, I should say. The answer is yes. Because remember, the second derivative was negative 2 over 9 x to the power 5 over 3. Because 5 is an odd number. If I put a negative number inside there, it remains negative. So I put a negative number inside there and I cube root it. It's going to stay negative. So my second derivative will remain negative. If x is positive, positive number raised to the fifth, still positive. Cube root of a positive number, still positive. Because they have different signs, that means at x equals 0, then there's a point of inflection by definition.
Wouldn't they both be the same sign though, because it's -2 on top?
No, because if the bottom is negative, then they cancel. You're right. Then this one here, the bottom would be negative. So we have -2 over the bottom being negative. So this would be positive, which is what it says. If the bottom number is negative and negative, so we have a concave up. On this side, when x is positive, it remains positive. So negative over positive remains negative. It's concave down.
Thank you.
No, great. That was a super great question. I totally forgot about the -2 on top. I was just too focused on the bottom. But yeah, that -2 on top does change things. Because when the bottom is negative and the top is negative, they both cancel out. So when x is negative, it's concave up. When x is positive, the top is negative, bottom is positive, it's concave down. So because of the opposite concavities, there has to be a point of inflection wherever they intersect. That's at x equals 0. A particle moving along, okay, A particle moving along a horizontal coordinate line with the position function 2t cubed minus 14t squared plus 22t minus 5, where t is greater than equal to 0. Find the velocity, the acceleration, and describe the motion. How do we find velocity? Yeah, it's the first derivative of our position function, which makes it 6t squared minus 28t plus 22. Remember, t is still greater than 0. We're describing the motion. So what we have to do is look at the values and where it's positive and negative. So factor this one out. Do they have anything in common? A 2. So let's factor this rest of it. Since the leading term is not 1, put it in the first part. We'll get rid of it later. The second sign's a plus. The only way that's a plus is if the signs are the same. They're both the first sign, so they're both minuses. Take the first, the A and C terms, and multiply them. 3 times 11 is 33. Give me two numbers when I multiply equal 33. When I add them, I get 14. 11 and 3. Since they're both the same signs, it doesn't matter where I put them. Now, take these, and can I factor anything out of the first one? No. Can I factor anything out of the second one? A 3, which leaves me t minus 1. Whatever I factor out of the second stage, I remove, delete it. There is our factor. So what are our critical values? We have the intervals. Our critical values are at 11 over 3 and at positive 1. So my intervals are from negative infinity to 11 over 3, 11 over 3. I got those backwards actually. What? 11 over 3. 3 goes in 11 3 times with 2 left over. So it's negative infinity to 1. 1 to 3 and 2/3. And then 3 and 2/3 to infinity. So my critical points are at 1 and 3 and 2/3. Pick a test value. Between negative infinity and 1, I pick 0. Between 1 and 3, I pick 2. And then here I pick 4. Those are my test values. I plug those in the second derivative. The first derivative, I'm sorry, first derivative. And what's happening? If I plug in 0 to my first derivative in this one, which is 2, 3t minus 11t minus 1. If I plug in 0, what do I get? Will it be positive or negative? Yeah, I get negative 11 times negative 1 is positive 11 times 2. I get 22, which is greater than 0. So it's increasing. In that interval, it's increasing to the right. How do I know it's increasing to the right? Because it's increasing. At 2, when I plug in 2 inside there, I get 2 times 6 minus 11, 2 minus 1. So we have 2 times negative 5 times 1 makes it negative 10. Since it's going negative, it's decreasing to the left. And then at 4, 3 times 4 is 12 minus 11. 4 minus 1 is 3. So 2 times 1 times 3 is 6. It's positive. So it's increasing to the right. So that's what's happening with the velocity.
How do you get the left and right?
Increasing, decreasing. Because if it's going positive to the right, negative to the left.
Okay.
So my velocity was 6t squared minus 28t plus 22. The acceleration is the first derivative of velocity, which is 12t minus 28. So where does it equal 0? What's my point of inflection? So 12t minus 28 equals 0 at 12t equals 28. T equals 28 divided by 12. Four goes in both of them. 4 goes in 28 7 times. 4 goes in 12 3 times. So my point of inflection occurs at 7/3. So what's concavity on both sides of those? For the acceleration, I have t equals 7/3. So from negative infinity to 7/3, and I have from 7/3 to positive infinity. I'll use 0 there. 7/3 is 2 1/3, so I'll use 3. The equation was 12t minus 28. So at 0, it's negative 28. Since it's negative, it's concave down. And at 3, we get 12 times 3 minus 28. So it's 36 minus 28 is 8. It's greater than 0, so it's concave up. Any questions so far? How we use the first and second derivatives? Derivatives? Can we use the second derivative test for local extrema? Remember, what do we know so far? Extremas occur when? When the first derivative is equal to 0. So if the first derivative equals 0, that's either a maximum or minimum. If the second derivative at that same value is negative, what does that mean at that point? Is it a maxima or a minima? If it's 0 here, what does it mean when it's negative? It's concave down, right? So it has to be a maximum. Very good. And number 2, if the first derivative is equal to 0 and the second derivative is positive, it means we have a concave up, which means we have a minimum. And if the first derivative at some value equals 0 and the second derivative also equals 0, what happens there? Is it a max or a min? Or neither? It can't be either, because when it's 0, it's a point of inflection. That's when it's, you can say it's either both concave up, concave down, or neither concave up. So it's neither. Next example. Example 8. Sketch this graph. Oh no, that means we're going to have to put everything we know from algebra and calculus on the table. So it's asking us, well, let's figure out what do we need to graph this? Well, let's look at, can we find the x-intercept? Can we find the y-intercept? Let's start with the basics first. What do we know about the graph so far? What degree is it? How many solutions are we going to have? We're going to have at most 4 solutions. Remember, why do I say at most 4 solutions? Well, yeah, because if degree is 4, that means we can have 4 solutions. We can have 3 solutions. We can have 2 solutions. We can have one solution, or we can have no solutions. But you have to have at least, I mean, you don't have you have no solutions or anything. If it's odd, then you have to have at least one solution. Even degrees can have no solutions because they both go the same direction. But we do know it opens up because of the coefficient, leading coefficient. All right. Do we know what the x-intercepts are? Can we figure it out? Yeah. Using Descartes rule of signs and, well, using Descartes rule of signs, we're going to have two positives and no negatives. So here's what's going to happen. We're going to have two positives, no negatives, and two imaginary or complex or radical, because they have to happen in conjugate pairs. Or I can have no positives, no negatives, and four imaginary or radical solutions. Which tells us we can either look like this or we can look like this. That's what the Descartes rule of sign tells us, because we have one sign change, two sign changes. So either going to have two or zero solutions, positive solutions. And the reason we have no negative solutions is because in front of the odd exponents, change the sign, and they're all positive, no sign changes. So we have no negative answers. Okay, what else can we find? Take the first derivative, set it equal to 0. What's that going to find for us? The vertices. And it's going to find for us where it's increasing or decreasing. We can find intervals like that. The second derivative, set equals 0, will have the point of inflection. And the second derivative will also tell us where it's concave up, the intervals, where it's concave up, concave down. So it's going to sketch the graph for us. So what do we know about the graph so far? Only thing we know by looking at the graph is what? Do you know any points on there? We know the y-intercept, the constant. So that's all we can do there. So we take the first derivative. 4x cubed minus 12x squared. Set that equal to 0. So we have 4x squared, x minus 3. So x is at 0 and x is at 3. So when x is 0, that means this is going to be a vertex. And there's going to be another vertex somewhere on this line. So we can look at this. When x is 0 and when x is 3, from negative infinity to 0, from 0 to 3, and then from 3 to infinity. This is for my first derivative. Where is it increasing? Where is it decreasing? So when x is -1, when x is 1, and when x is 4. Plug those into my first derivative. And all I want is a sign. I don't care about the number. So when x is -1, that was squared, makes it a positive. -1 minus 3 makes it -4. So this is going to be negative. So it's decreasing. So we know from the left of this, it's decreasing. But since that's a vertex, it's got to have a curve of some sort. Between 0 and 3, when x is 1, 4, -3 is -12. It's negative. It's also decreasing. Since that's a vertex, it has to have up of some sort. This is a vertex down here somewhere. I'm guessing this last one is going to be increasing. So that's going to be positive. 4 minus 1 is positive. So that's going to be positive. So it's increasing. So from this side, it has to go up. So this is what I'm guessing my graph's going to look like. Let's look at the second derivative test. If the first derivative was 4x cubed minus 12x squared, the second derivative is 12x squared minus 24x. Set that equal to 0. We got 12x, x minus 2. So it equals at 0 and at 2. We have a point of inflection. So at 0, we also had a vertex. So at 0, it was concave. Well, let's see the concavity first. So at 0 and at 2, let's see what the concavity looks like. From negative infinity to 0, from 0 to 2, and 2 to infinity. X equals -1, x equals 1, and x equals 3. So the second derivative, when x is -1, that's negative, that's negative. So negative, negative makes it a positive. So that's concave up. At +1, that's positive, that's negative. So it's negative, it's concave down. At 3, that's positive, so it's positive, so it's up. Which is exactly what I thought. It's concave up until 0, when there's a vertex. So it has to be down. Then it goes concave down from here. And then from this point, it's concave up. So there's your graph. So that's how we use the first and second derivatives to figure out what's going on. All right, let's do another one. Example 9. Sketch this function. X plus 1 squared, 1 plus x squared. Okay, we have a rational equation now. Since we have a rational equation, now we have to look for asymptotes. So here we look at, we're going to try to find x-intercepts, y-intercepts, vertical asymptotes. Oh, that's 4. Horizontal asymptotes, oblique asymptotes, and then we can go on with our first derivative and then our second derivative for concavity and increasing. Find intervals. And then we'll sketch our graph over here. So do we have any x-intercepts? How do we find x-intercepts? Set y equal to 0. So we set this equation equal to 0. The only way a fraction can equal 0 is if the top is equal to 0. So when you set the top equal to 0, we have an x-intercept at -1. Do we have a y-intercept? Yeah, set all the x's equal to 0, so you have 1 over 1. So we have a y-intercept at 1. Do we have a vertical asymptote? How do you find the vertical asymptote? Set the bottom equal to 0. Can the bottom ever equal 0? No, because it's plus, and this is always even. So it can never be negative. So no vertical asymptotes. Do we have a horizontal asymptote? If so, what is it? You can't just say yes or no. That's a 50-50 shot. Anybody can guess that. Impress me with an answer. So you didn't know, you just took a guess. What determines horizontal asymptotes? Well, the degrees of the leading term. What's the degree of the numerator? 2. What's the degree of the bottom? Since the degrees are the same, you look at the coefficients. What's the coefficient of the top one? 1. The bottom? 1. 1 over 1 is 1. So the horizontal asymptote is the line y equals 1. So we don't have any oblique asymptotes. We have a horizontal asymptote. So what vertices do we have? That's what this one tells us. So now we got to take the first derivative. Since we have a quotient, we got to use the quotient rule. F of G, F prime, G prime. So F is X plus 1 squared. G is 1 plus X squared. 2x plus 1 times 1, which is 2x plus 1. 2x. Since it's a quotient, we subtract it, so we have on top 2x plus 1 times 1 plus x squared minus 2x x plus 1 squared, all over the denominator squared. What are my critical points? We have to first combine all that stuff. So on the bottom, we have 1 plus x squared squared. All right, let's start multiplying all this stuff together. So we have 2x plus 2 times 1 plus x squared, 2x, and we boil this one out, so it's x squared plus 2x plus 1. Two x times 1 is 2x. 2x times x squared is 2x cubed. 2 times 1 is 2, 2x squared. Minus 2x cubed minus 4x squared minus 2x. The bottom, leave it alone. 2x cubed minus 2x cubed cancel. We have negative 4x squared, positive 2x squared, so it's negative 2x squared. Negative 2x, positive 2x cancel. We have a plus 2. So that becomes 2, 1 minus x squared, 1 plus x squared. So my critical points are where 1 minus x squared equals 0. So that's x equals plus or minus 1. So at plus or minus 1, we have vertices. We also know that at x equals negative 1, we have an x-intercept. So this is also a vertex. So the graph has to look something like that, since it is a vertex. And at 1, what value is that going to have? So we plug 1 back in the original equation. 1 plus 1 is 2, so 2 squared is 4. 1 plus 1 is 2, so at 2. So we have a vertex there. So our graph's going to look, and we have a horizontal asymptote. So that means it's going to look like this. And that It has to look like this. So there's the graph. Do we even have to do the second derivative? Not really, but it's just a good way to test. You guys will say no because you don't want to take a derivative of this function. Let's do it anyway. It is a calculus course. Let's find the second derivative. So if the first derivative is, let me see, let's do negative 2x squared minus plus 2, 1 plus x squared squared. So the second derivative, quotient again. So we need f, which is negative 2x squared plus 2. G is 1 plus x squared squared. F prime is negative 4x. G prime is 2, 1 plus x squared times 2x, which makes it 4x, 1 plus x squared. It's a quotient, so subtraction. So negative 4x times 1 plus x squared squared minus negative 2x squared plus 2 times 4x 1 plus x squared. All over 1 plus x squared to the fourth, because it's squared squared. Yes, we have to fix the top. So we have negative 4x, 1 plus x squared squared becomes 1 plus 2x squared plus x to the fourth. Negative 2x times 4x is negative 8x cubed plus 8x distribute this negative 4 inside there. So we get negative 4x minus 8x cubed minus 4x to the fifth. 8 times 1, so it's negative 8x cubed plus 8x minus 8x to the fifth plus 8x to the cubed. Negative 4x minus 8x cubed minus 4x to the fifth. Change all the signs inside there, so it's plus 8x cubed minus 8x plus 8x to the fifth minus 8x cubed. Negative 8x, positive 8x cubed cancel. 8x to the fifth minus 4x to the fifth is 4x to the fifth minus 8x cubed minus 8x. Oop, minus 8x is minus 12x. 8x and 4x can combine. We can factor out a 4x, leaving with x to the fourth minus 2x squared minus 3. This is quadratic in form. So we have 4x. We can factor that one out. We have x squared minus 3 and x squared plus 1. X squared plus 1 and 1 plus x squared is the same thing, so one of those can cancel. So our simplified version is 4x x cubed minus 3 over 1 plus x squared to the third. So what are our critical points for our point of inflection? Where's my graph? Oh, there it is. The point of inflections occur. So we have the second derivative equals to 4x x squared minus 3, 1 plus x squared cubed. So x is equal to 0 and square root of x plus or minus square root of x. 3, I mean. So what happens there? At 0 and radical 3.
How did you get radical 3?
X squared minus 3 set it equal to 0.
What,
X squared equals positive
what,
3 squared.
what about the 1 plus x squared on the bottom?
Can that ever equal 0? What makes a fraction equal 0?
Oh, numerator.
Yes. Yeah, that's why we never worry about the bottom. So x equals negative 1, x equals 1, and x equals 2. So when x is negative 1, that stays positive on the bottom. So it's 1 minus 3 is negative. Negative and negative makes it positive. So that's I can't do negative one is my vertex. These are my point of inflections, yeah. So what's happening here? And I have negative 1 as a vertex, so I can't use that. So I can use, if I use a negative half and negative 2. Since my point of inflection is at 0 and my vertex is at -1, I have to see what happens on both sides of -1. So -2. That's 4 minus 3. It's positive, negative. So that's negative. So it's concave down at 1/2. Negative. That makes it -2. Makes it positive 1/2. So it makes it negative. So negative and negative makes it a positive. So it's concave up at 1. Use 1. I can't use 1 because it's also a vertex. So I got to cut that in half. So at positive 1/2 and at positive 2. So at positive 1/2, that's positive, that's negative. So this is going to be negative. So it's concave down at 2. That's positive, that's positive. It's going to be positive, so it's concave up. So it's going to be concave down, concave up, concave down, concave up. And that's exactly what we said in our picture. Our picture to the left of -1 is concave down. To the right, it's concave up. After our point of inflection, which is at 0, it's concave down and then concave up. So that's what it does. It helps us sketch our graphs and understand what's going on even better from there. On the packet I gave you, on the very last page, I gave you the behavior chart. This summarizes the first and second derivatives, how it affects shapes of curves. If it's differentiable, smooth, connected. So if the first derivative is positive, it's an increasing function. If the first derivative is negative, it goes decreasing function, goes down. If the second derivative is positive, it's concave up. It can look like this. If it's an increasing or decreasing function. Second derivative is negative, it's a concave down, depending if it's increasing or decreasing functions. Where it equals 0 is the point of inflection on both sides, different concavities. First derivative, if to the left of it is positive, to the right is negative, that means it's a maximum. If to the left is negative to positive, then it's a minimum. So this pretty much everything we talked about today. And then some. I never thought that section was going to take 2 full days. But there you have concavity and curve sketching. Because we think about it, we went through not only calculus, the first, second derivatives, what they're used for, but we also looked at algebra, what we did in algebra, just looking at the function, what is a vertex, calculating the values of it. So there's a lot of extra parts there. Next time, we're going to look at indeterminate forms. What are indeterminate forms? Remember, we did this at the beginning of the semester. When you take a limit of a function, of a rational function, and you get 0 over 0, or if you get infinity over infinity, or if you get 0 times infinity, or if you get a number to the power infinity. All these are indeterminate forms. Bless you. That's what we'll talk about next time. Tomorrow. Actually, you guys want to take off tomorrow, or are you okay? You want to meet tomorrow? We have 5 weeks left, and we have something like 9 topics to discuss. So we're looking at finishing in 2 weeks, no matter how we look at it. So what do y'all want to take tomorrow off, or? Well, I it's my final exam for my